What if I told you that right now, at this very moment, the light hitting your eyes isn't just allowing you to see these words. It's actively creating the relationship between cause and effect in your universe? Here's something that will shatter everything you thought you knew about reality. In 2022, a team of physicists at the University of Vienna, led by Dr. Philip Walther, demonstrated experimentally that the causal order of events, what happens before and what happens after, can exist in a quantum superposition. But here's the truly mind-bending part. Light was the key to making this happen. We've always assumed that cause comes before effect. You flip a switch, then the light turns on. You throw a ball, then it breaks a window. This seems so fundamentally obvious that we never question it. But what if the very thing that allows us to perceive causality, light itself, is actually creating, bending, and in some cases, completely scrambling the cause and effect relationships we take for granted? Right now, photons from your screen are entering your eyes, and the information they carry about now left that screen 8 nanoseconds ago if you're sitting 2 feet away. But those photons don't experience time at all. From their perspective, they're emitted and absorbed simultaneously. So when we talk about light creating cause and effect, we're not speaking metaphorically. We're talking about the literal mechanism by which the universe establishes what comes before and what comes after. And here's what should terrify and excite you in equal measure. Recent experiments have shown that we can manipulate this mechanism. We can create situations where effect appears before cause, where causality flows backward, and where the very concept of before and after becomes meaningless. Before we dive into this reality-shattering journey, do me a favor, hit that like button and subscribe, because what you're about to learn will change how you perceive every single moment of your existence. And I'm genuinely curious. Drop a comment telling me what country you're watching from and what time it is where you are right now. Because by the end of this video, you'll understand why that question is far more complicated than it seems. Let's start with something that seems simple. What is light, really? You've probably heard that light is both a wave and a particle, right? That it's photons, that it moves at the speed of light, obviously, and that nothing can go faster. But here's the first twist that most people never learn. Light isn't actually moving through space the way you think it is. When James Clerk Maxwell unified electricity and magnetism in 1865, he discovered something extraordinary in his equations. Light was an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields. But here's what blew his mind. His equations predicted that this wave would travel at exactly 299,792,458 meters per second, no matter what. Not relative to the observer or relative to its source. Just that speed, always, in every direction, under all circumstances. Think of it like this. Imagine you're on a train moving at 50 miles per hour. And you throw a ball forward at 20 miles per hour. To someone standing on the ground, that ball is moving at 70 miles per hour, the speed of the train, plus the speed of your throw. That's how we expect everything to work. But light doesn't play by these rules. If you're on that train and you shine a flashlight forward, someone on the ground measures that light moving at exactly the speed of light. And impossibly, you also measure it moving at exactly the speed of light relative to you. The speeds don't add up. This isn't just weird. This is reality telling us something profound. Light exists in a fundamentally different relationship with space and time than everything else in the universe. Now, let's talk about cause and effect in the classical sense, before we start breaking it. Causality seems straightforward. One event causes another event. You drop a glass, it falls, it hits the ground, it shatters. Each step follows the previous one in a clear sequence. This is called the light cone structure of spacetime, first described by Hermann Minkowski in 1908, building on Einstein's special relativity. Here's how it works. Imagine a graph where one axis is space and the other is time. Any event, let's say, you snapping your fingers right now, occurs at one point on this graph. The light from that snap expands outward in all directions at the speed of light, forming a cone shape if we trace it through time. This is your future light cone. Everything inside this cone can potentially be affected by your finger snap, because light, or any signal, from that event can reach those points in spacetime. Similarly, there's a past light cone. Everything that could have sent light or information to reach you at the moment you snapped your fingers. Everything outside these cones, it's causally disconnected from your snap. It can't affect you, and you can't affect it, because no information can travel faster than light. This structure seems to create an ironclad rule. Cause must come before effect, and they must be connected by something light, sound, physical contact, anything traveling at or below the speed of light. But here's where things start getting strange, and this is your first major mind-blown moment. The very light that enforces this causal structure doesn't experience it. From a photon's perspective, if we can even use that phrase, there is no journey. Einstein's equations tell us that as you approach the speed of light, time slows down relative to a stationary observer. This is called time dilation, and it's been proven thousands of times. We have to account for it in GPS satellites, or your navigation would be off by miles. But at the speed of light, time dilation becomes infinite. A photon emitted from a star 13 billion light years away and absorbed by your eye right now experiences zero time between those events from its own reference frame. To that photon, emission and absorption are simultaneous, the same event. Think of it like this. Imagine you're watching a movie of someone's entire life, from birth to death. Now imagine you could compress that movie down to a single frame, where birth and death happen at the exact same instant. That's what the universe looks like from a photon's perspective. This creates a paradox. Light is the messenger that establishes causal relationships across space and time, yet light itself exists outside the flow of time. The medium that creates before and after for the rest of us doesn't experience before and after itself. So how does this actually create cause and effect for us? Let's get specific. When you see an object, let's say you're looking at your hand right now, photons are bouncing off your hand and entering your eyes. These photons carry information about the state of your hand at the moment they left its surface. When they hit your retina, they trigger a cascade of chemical and electrical signals that your brain interprets as hand. But here's the critical part. The causal relationship between hand exists in certain position, and brain perceives hand in certain position is established by the journey of those photons. Without light or some other signal, there would be no causal connection. Your hand could be anywhere, doing anything, and you'd have no way of knowing. This might seem obvious, but stay with me. What this means is that causality isn't a property of the objects themselves. It's a property of the information exchange between them, and light is the primary carrier of that information in our universe. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, published a paper pointing out what they thought was a flaw in quantum mechanics. They described a thought experiment where two particles could be entangled, such that measuring one instantly affected the other, even if they were light years apart. Einstein called this spooky action at a distance, and argued it proved quantum mechanics was incomplete, because it seemed to violate causality. Information would have to travel faster than light. Here's what will blow your mind. Einstein was wrong, and the reason he was wrong reveals something so profound about how light creates causality that once you understand it, you'll never look at reality the same way again. But to get there, we need to dive deeper into the quantum realm. What happens when we look at light not as a classical wave or particle, but as a quantum object? In 1905, Einstein himself, yes, the same Einstein who was later troubled by quantum mechanics, proposed that light comes in discrete packets he called light quanta, now known as photons. He did this to explain the photoelectric effect, where light hitting a metal surface could knock electrons loose, but only if the light was above a certain frequency. This discovery earned him the Nobel Prize in 1921. But photons are deeply weird. They're not little billiard balls of light. They're excitations of the electromagnetic field. Think of them like ripples in a pond, except the pond is the fundamental fabric of reality itself. Here's where it gets interesting for causality. A single photon exists in a superposition of all possible paths it could take from point A to point B until it's detected. This isn't speculation. It's the foundation of quantum electrodynamics, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the 1940s, work that earned them the 1965 Nobel Prize. Feynman showed that to calculate the probability of a photon traveling from source to detector, you have to add up contributions from literally every possible paths that go straight, paths that zigzag, paths that loop around, even paths that go backward in time. Each path contributes to the final probability amplitude. Let me make this concrete with an analogy. Think of light like water flowing from a mountain to the ocean. In classical physics, we'd say the water follows the path of least resistance, down the mountain, into streams, into rivers, to the sea. One path, determined by gravity and geography. But quantum light is like water that flows along every possible route simultaneously down the obvious streams, but also percolating through soil, evaporating and raining back down, even flowing uphill through capillary action in plants. The path the water takes is the sum of all these possibilities, weighted by how likely each route is. Now here's the kicker. Until you observe which path the photon took, it hasn't taken any specific path. It's taken all of them. The causal relationship between photon emitted here and photon detected there isn't a single line through spacetime. It's a quantum blur of all possible causal connections, collapsing into one definite outcome only when observed. This means that the cause and effect relationship created by light is fundamentally probabilistic and undefined until observation occurs. Light doesn't just transmit causality. It creates causality through the act of being observed. In 1978, physicist John Wheeler proposed one of the most mind-bending experiments in quantum mechanics, the delayed choice experiment. It was actually performed in 1984 by Carroll Alley and his team at the University of Maryland, and the results confirmed something shocking about the nature of causality. Here's the setup. Imagine you send a single photon toward a half-silvered mirror, a mirror that reflects 50% of light and lets 50% through. In quantum mechanics, the photon enters a superposition of both reflected and transmitted until detected. It literally takes both paths simultaneously. Now, Wheeler asked, what if we decide whether to measure which path or wave interference, AFTE, or the photon has already passed the mirror, but before it's detected? Classical logic says the photon's decision about whether to act like a particle, taking one definite path, or a wave, taking both paths and interfering with itself, should be made when it hits that mirror. But Wheeler's experiment showed that our choice of measurement determines what the photon did in the past. Think of it like this. Imagine you're watching security footage of someone entering a building. You can choose to watch the front door camera or the back door camera, but not both. And somehow, impossibly, your choice of which camera to watch determines which door they actually entered, even though they entered the building hours before you made your choice. This is where light starts to break causality as we understand it. The delayed choice experiment suggests that the causal relationship between source and detector isn't fixed until the detection occurs. The future measurement affects what happened in the past. But wait, doesn't this create paradoxes? If future measurements can affect past events, couldn't we send information backward in time? Couldn't we create contradictions, like the grandfather paradox? Here's the subtle but crucial point. No. And this is where the genius of quantum mechanics shines through. While the measurement choice affects the photon's past behavior, You can't use this to send information backward in time. The results of any individual measurement are random. You can only see the effect of your measurement choice in the statistical pattern of many measurements. By the time you've performed enough measurements to see the pattern, it's too late to affect any decisions in the past. It's like this. Imagine you could influence whether a coin in the past came up heads or tails, but you could only see the result after flipping that same coin 1,000,000 times and analyzing the statistics. By then, the past moment you're trying to influence is long gone. Light creates causality, but it does so in a way that prevents paradoxes through the fundamental randomness of quantum mechanics. And if you think that's as weird as it gets, let me tell you, we haven't even touched on quantum entanglement yet. Because when two photons become entangled, the relationship between cause and effect doesn't just get weird, it gets potentially non-existent. What I'm about to show you will make you question whether causality exists at all. Remember how Einstein called quantum entanglement spooky action at a distance? Let's understand why he was so bothered by it, and why modern experiments have proven that the spookiness is real. When two photons are entangled, they form a single quantum system, even if separated by vast distances. Measure a property of one photon, say, its polarization, and you instantly know the polarization of the other, even if it's on the other side of the galaxy. The correlation is perfect, instantaneous, and has been verified in countless experiments. The critical experiment came in 1982, when Alain Aspect and his team in France tested Bell's inequalities mathematical constraints that any local causal theory must obey. Local means that objects can only be influenced by their immediate surroundings, not by distant events. Causal means that influences propagate at or below the speed of light. Aspect's experiment showed that entangled photons violate Bell's inequalities. The correlations between the photons' properties are stronger than any local causal theory can explain. This work eventually contributed to Aspect receiving the Nobel Prize in 2022, along with John Clauser and Anton Zeilinger for experiments with entangled photons. So what does this mean for causality? Here's the mind-blown moment. When you measure one entangled photon, you're not causing the other photon to take on a specific state. You're not sending a signal faster than light. Instead, the two measurement events are correlated in a way that transcends cause and effect as we normally understand it. Think of it like this. Imagine you have a pair of magic coins. Whenever you flip one and it comes up heads, the other always comes up tails, no matter how far apart they are. But here's the weird part. Neither coin decides what it's going to be until you flip it. And when you flip yours, you're not sending any signal to the other coin. Yet the correlation is perfect. This is non-local correlation without causation. The two events measuring photon A and measuring photon B are correlated, but neither causes the other. They're both caused by the earlier event that created the entanglement in the first place. This suggests that causality isn't always a simple chain of one event causing the next. Sometimes, a single cause can create multiple effects that are correlated with each other, but don't cause each other. Light, through entanglement, can create these causal correlations. But here's where it gets even stranger. In 2012, physicists at the University of Vienna, led by Xiusong Ma, performed an experiment where they created entanglement between photons that never coexisted in time. Here's how it worked. They created an entangled pair of photons. Call them photons 1 and 2. Then they measured photon 1, destroying it. After photon 1 was gone, they created photon 3 and entangled it with photon 2. Finally, they created photon 4 and entangled it with photon 3, then destroyed photons 2 and 3 together in a special measurement. The result? Photons 1 and 4 were entangled, even though they never existed at the same time. Photon 1 was destroyed before photon 4 was created, yet they shared the perfect correlations of entangled particles. This is called entanglement swapping, and it raises a profound question. If two photons can be entangled without ever coexisting, what does that say about causality? How can something that doesn't exist anymore be correlated with something that doesn't exist yet? The only way to make sense of this is to realize that the causal structure isn't about individual photons at specific moments in time. It's about the relationships between measurements, which form a web of correlations that transcends our ordinary notion of past, present, and future. Let me give you another analogy to wrap your head around this. Think of causality like a novelist story where one event leads to another in sequence. You read page 1, then page 2, then page 3, and the story unfolds in a linear way. But quantum entanglement is more like a crossword puzzle. The answer to 3 down constrains the answer to 7 across, which constrains 15 down, which constrains 3 down again. The constraints form a web of relationships, and the solution to the puzzle isn't found by solving one clue and then the next in sequence. You have to consider all the clues simultaneously, and they all constrain each other. Entangled photons create a puzzle-like structure of correlations across spacetime, rather than a linear story of cause and effect. Light isn't just carrying information from one place to another. It's weaving a web of relationships that defines what can happen where and when. Now, I know what you're thinking. This is fascinating, but how does this actually affect me? How does quantum weirdness with photons relate to my everyday experience of cause and effect? Hold that thought, because we're about to connect these abstract concepts to something far more personal and immediate. But first, we need to understand one more crucial piece. What happens when we try to reverse causality entirely? What if light could travel backward in time? Not in some sci-fi sense, but in a way that's consistent with the actual laws of physics. Richard Feynman, who we mentioned earlier, realized something extraordinary in the 1940s. When you write down the equations for a photon traveling forward in time, you can also interpret them as describing a photon with negative energy traveling backward in time. Mathematically, both descriptions are equivalent. In fact, Feynman's approach to quantum electrodynamics treats antimatter particles like positrons, the antimatter version of electrons, as ordinary particles moving backward in time. A positron moving forward in time looks exactly like an electron moving backward in time. Now, this doesn't mean we can send information to the past or create time travel paradoxes. But it does mean that the mathematical structure of light and causality is symmetric in time. The equations don't care which direction time flows. In 2017, a team led by physicist Yakir Aharonov at Chapman University proposed and experimentally verified something called retrocausal quantum mechanics. The idea is that the state of a quantum system is determined not just by its past, where it came from, but also by its future, where it's going to. Imagine you're driving a car, and your path is determined not just by where you've been, but also by where you're heading. If you know someone is ultimately going to arrive at a specific destination, you can make better predictions about where they are right now, even without knowing their exact starting point. In the same way, if you know how a photon is going to be measured in the future, you can make better predictions about its behavior in the present. The future measurement constrains the present state. This is sometimes called the two-state vector formalism, and experiments have confirmed its predictions. Think of it like this. You're watching a river flow. Normally, you'd say the water at point A causes the water at point B to flow. The upstream causes the downstream. But what if the downstream also influences the upstream? What if a waterfall downstream creates a pressure wave that propagates backward, affecting how the water flows upstream? That's analogous to retrocausality in quantum mechanics. One of the most beautiful examples of this comes from the quantum eraser experiment, first proposed by Marlin Scully and Kai Drull in 1982, and performed in various forms since then. Here's the basic setup. You send photons through a double-slit apparatus, 2 narrow openings. If you don't measure which slit each photon goes through, you get an interference pattern on the screen. showing that each photon went through both slits and interfered with itself. But if you do measure which slit each photon goes through, the interference pattern disappears. Each photon acts like it went through one slit or the other, not both. Now here's the twist. What if you measure which slit each photon went through, but then you erase that information before looking at the screen? Scully and Droll showed that if you erase the which path information, the interference pattern comes back, but only for the subset of photons where you erase the information. The mind-blowing part: you can choose whether to erase the information after the photon has already hit the screen. Your future choice of whether to erase determines whether the photon that already hit the screen contributed to an interference pattern or not. The future affects the past behavior of the photon. Now, let me address the obvious question. If the future can affect the past, why can't I use this to send information backward in time? Why can't I warn my past self about mistakes I'm about to make? Here's the crucial limitation. You can't choose the outcome of any individual measurement. Each photon's contribution to the pattern is random from your perspective. You can only see the effect of your future choice when you gather enough data to reveal the statistical pattern. And by then, you're already in the future. You can't go back and change anything. It's like trying to send a message by influencing the weather. Sure, you might be able to make it slightly more likely to rain on a given day, but you can't control whether any specific raindrop falls, so you can't encode information that way. The universe allows retrocausality, the future influencing the past, but prevents it from being used to create information paradoxes. Light can flow backward in time in a sense, but only in a way that preserves consistency. So light creates causality going forward, connects distant events through entanglement, and even influences the past through retrocausality. But we still haven't addressed the most mind-bending possibility. What if the causal order itself, the sequence of which events come before which other events, isn't fixed? What if light can exist in a superposition of different causal orders? That's where we're going next. And trust me, this is where your intuitions about reality will completely collapse. In 2015, a group of physicists, including Giulio Chiribella and others, formalized something called indefinite causal order situations, where the order of events is in quantum superposition. Event A might come before event B, or event B might come before event A, and both possibilities exist simultaneously until measured. This isn't just theoretical. In 2019, the team led by Philip Walther at the University of Vienna that I mentioned at the start actually created this in the lab using photons and beam splitters in a configuration called the quantum switch. Here's how it works. You have two operations, call them A and B, that can be performed on a photon. In the classical world, you either do A then B, or you do B then A. The order is definite. But Walther's team created a quantum switch where a control photon determined the order. If the control photon went one way, operation A happened before B. If it went the other way, operation B happened before A. But they put the control photon in a quantum superposition of both paths, which meant the operations A and B happened in a superposition of both orders simultaneously. Let me make this concrete. Imagine you're baking a cake, and you have two steps: mixing the ingredients and heating the oven. Normally, the order matters. You need to mix before you can bake. But what if you could exist in a superposition where you both mixed then baked and baked then mixed at the same time? And only when you took the cake out did reality decide which order you actually performed the steps in. That sounds impossible, right? But this is exactly what happens with photons in the quantum switch. The photons experience both causal orders simultaneously, and only when measured does one definite order emerge. This has profound implications. It means that causality, the fundamental structure of what comes before and what comes after, isn't a fixed feature of reality. It's a quantum property that can be in superposition. Light, being a quantum object, can literally exist in states where the causal order of events is undefined. And since light is the primary means by which causal relationships are established in our universe, this means the causal structure of spacetime itself can be in superposition. Now, why does this matter? What can you do with indefinite causal order? One application is quantum computing. It turns out that algorithms using indefinite causal order can solve certain problems more efficiently than algorithms with definite causal order. In 2018, researchers showed that quantum communication protocols with indefinite causal order can transmit more information than classical protocols. But beyond practical applications, this fundamentally changes how we understand cause and effect. We've always thought of causality as the bedrock of physical law, the one thing that's absolutely fixed. But if causality itself can be in superposition, then what is causality really? Here's a way to think about it. Causality isn't a property of events themselves. It's a relationship that emerges from the quantum state of the universe. When light connects two events, it doesn't necessarily establish a definite causal order. It can establish a quantum superposition of causal orders, and only through observation does one order become definite. Let me give you an analogy that might help. Think of causality like the plot of a story. In most stories, the plot unfolds linearly. This happened, then that happened, then that happened. But in some experimental fiction, authors play with narrative structure. You might read chapter 3 before chapter 2, or the ending might loop back to the beginning, or multiple timelines might run in parallel. Now imagine a book where the order of chapters is in quantum superposition. You're simultaneously reading it in every possible order until you measure the sequence by trying to summarize the plot. Only then does the book collapse into having been read in one definite order. That's what indefinite causal order means for light and events connected by light. The story of cause and effect isn't written linearly. It exists in a superposition of all possible storylines until observation forces it to become definite. Now, at this point, you might be feeling like reality is slipping away from you. If causality isn't fixed, if the order of events can be undefined, if the future can influence the past, then what can we rely on? What is real? Here's where we need to zoom out and look at the bigger picture of what light reveals about the structure of spacetime itself. Because the answer to, does light create cause and effect, is intimately connected to the question, what is time? To understand how light creates causality, we need to understand what time actually is. And this is where we return to Einstein's revolutionary insight from 1905. Before Einstein, everyone assumed time was absolute, a universal clock, ticking away the same for everyone everywhere. Newton wrote that time flows equably without relation to anything external. 1 second for me is 1 second for you is 1 second everywhere in the universe. But Einstein realized this couldn't be true, because the speed of light is constant for all observers. If you're moving toward a light source, you don't measure the light approaching you any faster. If you're moving away, you don't measure it approaching any slower. It's always the same speed. The only way this can work is if time itself is relative, if moving clocks tick slower than stationary clocks, and if simultaneity, whether two events happen at the same time, depends on your motion. Here's a concrete example. Imagine two spaceships passing each other in space. On each ship, there's a clock. From the perspective of ship A, ship B is moving, so ship B's clock ticks slower. But from the perspective of ship B, ship A is moving, so ship A's clock ticks slower. Both perspectives are equally valid. This seems contradictory. How can both clocks be slower than the other? The resolution is that slower is relative to what you consider now at different locations. The very concept of now across space is relative. There's no universal present moment. This is called the relativity of simultaneity, and it's crucial for understanding causality. Two events that are simultaneous for one observer happen at different times for another observer. But, and here's the key, the causal order is preserved. If event A can causally influence event B, if light or information can travel from A to B, then all observers agree that A comes before B light, moving at the ultimate speed limit, defines which events can causally affect which other events. Think of it like this. Imagine you're watching two performers in a theater, one on the left side of the stage and one on the right. Depending on where you're sitting, they might appear to move in sync, or one might appear slightly ahead of the other. Your perspective changes what appears simultaneous. But if one performer throws a ball to the other, all audience members agree on the order. Thrown first, caught second. The causal connection defines an absolute order that everyone agrees on. Now, here's where it gets really interesting. In 1908, Hermann Minkowski, who had been Einstein's math teacher, reframed special relativity in terms of spacetime, a four-dimensional fabric where space and time are interwoven. In this framework, the path of light forms the boundary between past and future. Your past light cone is all the events that could have sent light to reach you now. Your future light cone is all the events that you could send light to. And the boundary of these cones, the surface, is formed by the paths of light itself. This means light literally defines the causal structure of the universe. It's not just that light is one of many things that carry causal influence. Light, by moving at the cosmic speed limit, sets the boundary of what can cause what. Any event outside your past light cone couldn't have affected you. No information could have traveled from there to here in time. Any event outside your future light cone can't be affected by you. You can't send information there in time. Light creates a boundary, and causality lives inside that boundary. But here's something that will blow your mind. Spacetime isn't just a backdrop on which events happen. According to general relativity, Einstein's 1915 theory of gravity, spacetime is a dynamic, flexible fabric that bends and warps in response to mass and energy. And light, having energy, contributes to this warping. Every photon that travels through the universe slightly curves spacetime around it. The effect is tiny, unimaginably tiny for ordinary light, but it's real. This means light doesn't just move through spacetime. It shapes spacetime. And since the shape of spacetime determines causal structure, which events can affect which other events, light literally sculpts causality itself. It's like this. Imagine spacetime as a rubber sheet. Objects with mass create dips and curves in the sheet. That's gravity. Light, having energy, also creates tiny ripples and curves as it passes. These curves change the paths that other light and objects can take, which changes what can causally affect what. So light creates causality in a double sense. It defines the boundary of causal influence by moving at the speed limit, and it shapes the very fabric that determines how causal influences propagate. Everything we've discussed so far treats light as something that obeys the laws of physics. But here's a thought that should shake you to your core. What if we've got it backward? What if light doesn't obey the laws? What if light defines them? What if the properties of light are so fundamental that they determine the very structure of physical law itself? This is where we transition from physics to the philosophical implications of everything we've learned. There's a principle in physics called Lorentz invariance, the idea that the laws of physics are the same for all observers moving at constant velocities. This principle is what leads to special relativity, time dilation, and all the weird effects we've discussed. But here's something most people don't realize. Lorentz invariance is equivalent to the statement that the speed of light is constant for all observers. They're the same principle, just viewed from different angles. This means that the constancy of light speed isn't just one law among many. It's the foundation that determines the structure of all physical laws. Every equation in physics must be written in a way that respects the constancy of light speed, which means light's properties constrain what laws of physics are even possible. Think about what this means. Light isn't just obeying laws that exist independently. Light's nature is so fundamental that it determines what laws can exist. In 1962, physicist Eugene Wigner wrote a famous paper titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He marveled at how mathematical structures seemed to perfectly describe physical reality and wondered why this should be so. But there's an even deeper mystery. Why do the laws of physics have the specific mathematical structure they do? Why, for example, does electromagnetism obey Maxwell's equations specifically? One answer, suggested by modern approaches like string theory and quantum field theory, is that the structure of physical laws is determined by symmetry's fundamental invariances that nature respects. And one of the most important symmetries is Lorentz invariance, which is all about light. In a sense, light is the linchpin that holds the mathematical structure of physics together. Change the speed of light, or make it different for different observers, and the entire edifice of modern physics collapses. You'd have to rebuild it from scratch with different symmetries, different equations, different everything. So light doesn't just create cause and effect. It creates the very possibility of having consistent physical laws that define cause and effect. Let me give you an analogy. Think of physical laws as a Jenga tower, a structure built from many interlocking pieces. You might think light is just one block in the tower, but it's not. Light is more like the table the Jenga tower sits on. Change the fundamental properties of light, and you don't just remove one block, you tilt the entire playing field, and the whole tower has to be rebuilt according to different rules. This is why the speed of light shows up in E.E., Kyle's MC, even though that equation is about mass and energy, not light specifically. It's why the speed of light appears in equations about gravity, about quantum mechanics, about particle physics. Light's properties are woven into the very fabric of physical law. Now, here's where this gets truly philosophical. If light's properties determine the structure of physical law, and physical laws determine cause and effect, then in what sense does light create causality? One way to think about it, causality isn't a thing that exists independently, waiting for light to transmit it. Causality is a relationship structure that emerges from the properties of light. The fact that there is such a thing as before and after, that there is a direction to time, that there are events that can influence other events, all of this exists because light has the properties it does. In a universe where light behaved differently, say, if it had no maximum speed, or if its speed varied depending on direction, the very concept of causality would be different. We might not have a clear distinction between past and future. The entire structure of time might be different. So light doesn't create causality in the sense that it carries pre-existing causal influences from place to place. Light creates causality in the sense that its properties define what causality is. Now, I've been talking about light as if it's just photons and electromagnetic waves. But there's a deeper level we need to explore, because light is just one manifestation of something more fundamental, the quantum field. And when we understand light at this level, the question of whether it creates causality becomes the question of whether reality itself is fundamentally about information and relationships, rather than things and substances. This is where physics meets philosophy in the most profound way possible. Let's shift our perspective entirely. Instead of thinking about light as a thing, a wave or particle traveling through space, let's think about what light actually does. It carries information. When you see an object, light is carrying information about that object's location, color, and shape from the object to your eyes. When radio waves transmit a signal, they're carrying information. When X-rays image your bones, they're carrying information about internal structure. In 1948, Claude Shannon developed information theory, which treats information as a quantifiable thing measured in bits that can be transmitted, stored, and processed. Shannon showed that all communication systems, whether using light, electricity, sound, or anything else, obey the same fundamental principles. But here's what's interesting. Quantum information, carried by photons, has properties that classical information doesn't have. Quantum information can be in superposition simultaneously in multiple states. It can be entangled, correlated in ways that defy classical explanation. And as we've discussed, it can exhibit strange causal properties. In 2004, physicist Lucien Hardy proposed a radical approach to quantum mechanics based on information theory. He showed that the core principles of quantum mechanics, superposition, entanglement, measurement, can be derived from a few simple axioms about how information behaves. This suggests that quantum mechanics isn't fundamentally about particles and waves. It's about information, how it's structured, how it flows, how it's transformed by measurements. And if quantum mechanics is about information, and light is the primary carrier of quantum information in our universe, then light is the medium through which reality itself is structured. Causality, in this view, isn't about one physical event pushing on another physical event. It's about information flow, how knowledge about one event can propagate to other events. And light, as the primary information carrier, creates the pathways through which causal information flows. Think of it this way. Imagine reality as a vast computer network. Each event is a node in the network, and causal relationships are the connections between nodes, the cables carrying data. In this analogy, light is the network infrastructure itself. It's the physical layer that allows information to flow from node to node. But more than that, the properties of light, its speed, its quantum nature, its ability to be entangled determine what kind of network topology is possible. They determine how information can be routed, what kinds of correlations can exist between nodes, and what patterns of information flow are allowed. In this sense, light doesn't just create causality. It is causality. Causality is the pattern of information flow, and light is the medium of that flow. Now, here's a deep question. Is information physical, or is the physical world made of information? Physicist John Archibald Wheeler, who coined the term black hole and mentored many of the giants of quantum mechanics, proposed a principle he called it from bit. The idea is that every physical thing, every it, derives its existence from bits of information. In quantum mechanics, you can't separate the information about a system from the system itself. The quantum state is the information, and the information is the quantum state. They're not two different things with one describing the other. They're one and the same. If this is true, then light as quantum information isn't just describing physical reality. Light is physical reality, or at least one manifestation of it. And if causality is about information flow, and information is fundamental, then light creating causality isn't a metaphor. It's a literal description of how reality works. Now, we've been talking about all of this in abstract terms: photons, quantum mechanics, information theory. But how does this connect to your direct, immediate experience? How does the fact that light creates causality affect your everyday life and perception? This is where we get personal, because the answer has profound implications for how you experience time, make decisions, and understand your place in the universe. Let's bring this home. Right now, as you watch this video, light from your screen is entering your eyes. But there's something profound about this simple fact that you probably never considered. The light entering your eyes right now was emitted from your screen about 2 to 3 nanoseconds ago, assuming you're sitting a comfortable distance away. Your brain's visual processing takes about 200 milliseconds to interpret that light into conscious perception. This means that when you think you're seeing now, you're actually seeing the past, specifically about 200 milliseconds in the past. But here's the trippy part. From the photon's perspective, there is no time between emission and absorption. To the photon, leaving your screen and hitting your retina are the same event. Yet to you, there's a 200 millisecond journey of neural processing. This creates a strange situation. The mechanism that creates your sense of now, light carrying information, doesn't itself experience the flow of time. Your perception of causality and temporal flow is created by something that exists outside of temporal flow. Think about what this means for your experience of reality. You've probably had moments where time seemed to slow down during an accident, a thrilling experience, or a moment of intense focus. Or moments where time seemed to speed up hours, passing in what felt like minutes. These aren't illusions in the sense of being false. They're different modes of how your brain constructs temporal experience from the timeless information carried by light. Your brain receives a constant stream of photons, carrying information about the external world. But it doesn't present this information to your conscious mind as a raw stream. Instead, it constructs a narrative, a story, where events happen in sequence, where causes lead to effects, where time flows smoothly from past to future. But this narrative is a construction. The underlying reality, the photons arriving at your retinas, doesn't have this narrative structure. Your brain creates it. Here's an analogy that might resonate. Think about watching a movie. The movie is actually 24 still images per second, each slightly different from the last. But your brain doesn't perceive 24 separate images. It creates the illusion of smooth motion, of one moment flowing seamlessly into the next. Your experience of reality is similar. Light delivers discrete packets of information, individual photon absorptions, quantum events. But your brain weaves these into a continuous experience of reality, where time flows, where causes lead to effects, where you exist as a continuous self moving forward through time. The causality you experience, the feeling that one moment leads to the next, that your actions cause outcomes, is partially a construction built by your brain from the quantum information delivered by light. Now, this might sound like I'm saying your experience is an illusion, that causality isn't real. But that's not quite right. Your experience is real. It's just that it's not the whole story. Think of it like this. When you look at a painting, what you see is real. The colors, the shapes, the emotional impact, all real. But if you look closer with a magnifying glass, you see individual brushstrokes. Closer still with a microscope, you see molecules of pigment. None of these levels is more real than the others. They're different levels of description, all valid, all real. Similarly, the causality you experience in your everyday life, your decision to reach for a cup leading to your hand moving, is real at that level of description. But at a deeper level, it's quantum information carried by photons, creating correlations between brain states and muscle states, with no single definite causal path, but rather a quantum superposition of paths that your brain integrates into a coherent experience. Both levels are real. Light creates causality at the fundamental level, and your brain creates the experience of causality at the conscious level. They're both part of the story. Here's something that should change how you view your own decisions. When you make a choice, let's say you decide to pause this video and get a snack. That decision feels like it happens at a single moment. Your will causes your action. But neuroscience tells us something different. Brain activity associated with a decision can be detected up to several seconds before you become consciously aware of making the decision. The neuroscientist Benjamin Libet demonstrated this in the 1980s. This has led some people to conclude that free will is an illusion, that your conscious decision is actually a post hoc rationalization of unconscious processes. But here's another way to think about it. The causal chain isn't conscious decision gives. Brain activity gives action. It's distributed quantum processes in neurons, mediated by light and electromagnetic fields, gives integrated brain state, gives conscious experience of decision-making. Your conscious experience of deciding isn't the cause of your action in a simple, linear sense. It's part of a complex causal web where quantum information propagates through your neural network, creating correlations and patterns that eventually coalesce into both the action and the conscious experience of choosing that action. Light, carrying information between neurons at the quantum level, is creating the causal structure that gives rise to both your actions and your experience of willing those actions. This raises an even more profound question. If light creates the causal structure of your experiences, and if causality can be in superposition or can flow backward in time, what does that mean for consciousness, for your sense of self, for the feeling that you're a continuous being persisting through time? Hold on to those questions, because we're about to explore how light's role in creating causality intersects with the deepest questions about the nature of mind and self. We need to talk about the measurement problem in quantum mechanics, because it's intimately related to consciousness, observation, and the role of light in creating reality. Here's the issue. In quantum mechanics, a system exists in superposition multiple possible states simultaneously until it's measured. Upon measurement, the superposition collapses into one definite state. But what counts as measurement? What causes the collapse? The standard interpretation of quantum mechanics, developed by Niels Bohr and others in the 1920s, says that measurement is a macroscopic, irreversible interaction. But this is vague. How macroscopic? How irreversible? Some physicists, including Eugene Wigner and later Roger Penrose, have proposed that consciousness plays a role in collapse. The idea is that a quantum superposition only collapses when observed by a conscious observer. Now, this is controversial, and most physicists reject it. But here's why it's relevant to our discussion. If consciousness does play a role in quantum measurement, and if quantum measurements are what establish definite causal relationships, then consciousness would be part of how light creates causality. Think about it. A photon in superposition hasn't taken any definite path. It hasn't established a definite causal connection between source and detector. Only when observed, and if observation requires consciousness, does the causal connection become definite. In this view, light doesn't create causality on its own. Light creates potential causality, a web of possible causal connections in superposition and consciousness, actualizes specific causal paths by observing. It's like light sketches out all possible causal structures, and consciousness traces one particular path through that space of possibilities, making it real. Now, even if consciousness doesn't play a special role in quantum mechanics, and again, most physicists don't think it does, there's still a deep connection between consciousness and light-created causality. Your conscious experience is built from sensory information, and the vast majority of that information comes from light. Vision dominates human perception. Estimates suggest that 80% or more of the sensory information your brain processes comes from your eyes. This means that your conscious model of reality, including your sense of cause and effect, is primarily built from information carried by light. You see an event happen, then you see its consequence, and your brain infers causality. You see someone throw a ball, then you see it break a window, and you understand the causal connection. But this understanding is mediated by light. You're not directly perceiving the causality. You're perceiving light that carries information about events, and your brain constructs the causal narrative from that information. Here's a thought experiment that illustrates this. Imagine you're watching a video of a billiard ball collision. You see one ball rolling toward another, they collide, and the second ball rolls away. You perceive a clear causal relationship. The first ball caused the second to move. Now imagine the same video played in reverse. You see the second ball rolling toward the first, they collide, and the first ball rolls away. This looks almost as natural. The laws of physics are time-symmetric for this collision, so both directions look physically plausible. But your perception of causality has flipped. In the first video, ball A caused ball B's motion. In the reversed video, ball B caused ball A's motion. The information carried by light is the same, just time reversed, but the causal story your brain tells is different. This shows that causality isn't just in the light, it's in how your brain interprets the patterns of light over time. Light provides the raw material, but consciousness constructs the causal narrative. Now, let's go deeper. There's a philosophical position called panpsychism that suggests consciousness, or something like proto-consciousness, might be a fundamental feature of reality, present even in elementary particles. I'm not arguing for or against panpsychism here, but I want to point out something interesting. If information is fundamental, as Wheeler's It from Bit suggests, and if consciousness is fundamentally about processing information, then maybe consciousness and fundamental physics aren't as separate as we usually think. Light, as quantum information, has properties that seem almost proto-conscious. It knows about all possible paths simultaneously, superposition. It's correlated with distant partners instantaneously, entanglement. It responds to future measurements, retrocausality. These are metaphors. Of course, photons don't literally know or respond in a conscious sense. But the information processing properties of light share structural similarities with the information processing properties of consciousness. Maybe, just maybe, consciousness and the quantum information carried by light are two ends of a spectrum, different levels of the same fundamental phenomenon of information processing and integration. This is starting to feel almost mystical, and I want to be careful here. We're at the edge of what science can currently tell us, venturing into philosophical speculation. But these questions matter because they affect how you understand yourself and your place in reality. So let's get even more personal. What does all of this mean for your life? For your choices? For what matters? Let's take stock of where we are. We've learned that light doesn't experience time, yet creates our experience of temporal flow. Causality can be in superposition, reversed or indefinite. The future can influence the past in quantum systems. Information might be more fundamental than matter. Your conscious experience of causality is a construction built from quantum information. So what does this mean for how you live your life? First, it should give you a profound appreciation for the present moment. The now you're experiencing isn't a dimensionless point between past and future. It's a thick, constructed experience. Your brain integrating information from photons that left their sources at different times, processing them over hundreds of milliseconds, and presenting you with a coherent now. Every moment you experience is a minor miracle of integration and construction. Light from different sources, carrying information about events that happened at different times, all combined into your unified experience of this moment. When you really sit with this, when you realize that your now is a sophisticated construction built from timeless information carriers, it can give you a different relationship with time. Less rushing toward the future, less dwelling on the past, more appreciation for the constructed nature of the present. Second, the quantum nature of causality should change how you think about decisions and outcomes. In classical thinking, every decision leads deterministically to one outcome. You make choice A, outcome B follows with certainty if we knew all the relevant factors. But quantum mechanics tells us this isn't how reality works at the fundamental level. There's genuine randomness, not just lack of knowledge. And there's superposition, multiple potential outcomes coexisting until observation. Your decisions don't deterministically create one future. They shape the probability distribution over many potential futures. And in a sense, all those potential futures have a kind of quantum reality until you observe the outcome. This doesn't mean your choices don't matter, quite the opposite. It means your choices matter in a richer, more complex way than simple determinism would suggest. You're not just selecting one future from a fixed set. You're shaping the quantum probability space itself. Think of it like this. In a deterministic universe, making a choice is like selecting a book from a shelf. The book already exists with all its pages written. You're just choosing which predetermined story to read. But in a quantum universe, making a choice is like being a co-author. The general outline might be constrained by the setup, but the specific details emerge through the interaction between your choices and quantum randomness. You're not selecting a predetermined future. You're participating in its creation. Light, carrying quantum information about your choices and their outcomes, creates a web of causal possibilities. and your continued choices and observations select paths through that web. Third, the non-local correlations created by entangled light should change how you think about connection and separation. You and other people, other objects, other parts of the universe aren't separate in the way classical physics suggests. Every time you absorb a photon from the sun, which happens billions of times per second, you're becoming entangled with the sun. Every time you see another person, photons bouncing off them enter your eyes, and quantum information about them becomes part of your physical state. At the quantum level, you're constantly entangling with everything you observe. These entanglements typically decohere. Very quickly, the quantum correlations get scrambled by interactions with the environment. But for brief moments, you and everything you see are part of one quantum system connected by light. You're not a separate observer looking at an independent external world. You're part of a connected web, and light is the thread weaving you into that web. Now, I want to address something you might be thinking, this is fascinating, but does it really matter for my everyday life? Here's why it does, and why understanding light's role in creating causality is one of the most empowering realizations you can have. Let's get concrete about how understanding light's role in causality can change your life. First, time perception and productivity. You now know that your experience of time is constructed, and that this construction can be influenced. When you're bored, your brain is receiving less information, so it constructs a subjective experience where time drags. When you're intensely engaged, your brain is processing vast amounts of visual information, and time seems to fly. But here's the actionable part. You can deliberately manipulate your time perception by changing your visual environment and attention. Want a period of time to feel longer, more expansive? Seek out new visual experiences, new environments, new patterns of light and color. Your brain will process more information, and the period will feel subjectively longer in retrospect. Want time to pass quickly through something unpleasant? Reduce visual information. Close your eyes, zone out, let your visual processing idle. Your brain constructs less time from less information. Second, decision-making under uncertainty. Understanding that causality is probabilistic rather than deterministic should change how you approach decisions. Stop trying to predict the one correct outcome of your choices. Instead, think in terms of shaping probability distributions. Ask yourself, how does this choice change the landscape of possible futures? Not, what will definitely happen if I do this? This shift from deterministic to probabilistic thinking is more than philosophical. Studies in psychology and behavioral economics show that people who think probabilistically make better decisions under uncertainty. They're less prone to regret, less paralyzed by indecision, and more resilient when outcomes don't match expectations. You're not trying to control the future. You're trying to create favorable probability distributions. Knowing that quantum randomness means the specific outcome is unknowable, but the general shape of possibility space is influenceable. Third, presence and mindfulness. Many meditation and mindfulness practices emphasize being present and observing without judgment. Now, you understand why this is profound from a physics perspective. When you're observing the present moment, really observing, with attention to the sensory information carried by light entering your eyes, you're participating in the process by which quantum superpositions collapse into definite actualities. Your observation isn't passive. It's part of the mechanism that makes causality definite. This doesn't mean you have magical powers to control reality with your mind, but it does mean that conscious observation is a real physical process with consequences for the causal structure of your local reality. Being present isn't just psychologically healthy. It's physically participating in the creation of definite causality from quantum possibility. Fourth, connection and compassion. Understanding quantum entanglement and the way light creates webs of correlation should foster a sense of deep connection with others and with the environment. Every person you see, you're literally entangling with via the photons bouncing between you. Every landscape you observe, you're becoming quantum mechanically connected to, however briefly. This isn't mysticism, it's physics. And recognizing this interconnection, really internalizing it, naturally leads to greater compassion and care. You're not separate from the world you observe. You're part of it, connected by light. We're nearing the end of this journey, and I want to bring together everything we've explored to answer the original question as completely as possible. Does light create cause and effect? But more than that, I want to leave you with a new framework for understanding your place in reality. Let's bring it all home. Does light create cause and effect? After everything we've explored, here's the complete answer. Light creates causality in multiple, interconnected ways. At the foundational level, light defines the maximum speed of information propagation, which creates the light cone structure that determines which events can causally influence which other events. Without this speed limit, without light's special role in relativity, causality would have an entirely different structure, or might not exist at all in any recognizable form. At the quantum level, light carries information in quantum form superpositions, entanglements, indefinite causal orders. The causal relationships between events aren't simple, predetermined connections. They're quantum mechanical probabilities that exist in superposition until observation makes them definite. Light creates this quantum scaffolding of possible causalities. At the geometric level, light shapes spacetime itself. Through general relativity, the energy of light creates curves and warps in spacetime, changing the causal structure, which events can influence which others. Light doesn't just move through spacetime. It sculpts spacetime and therefore sculpts causality. At the information level, light is the primary carrier of information in our universe. Causality, understood as information flow, is therefore literally constituted by light. When we say event A causes event B, we often mean information about A reached B, and that information likely traveled as light. At the experiential level, your conscious experience of causality, your sense that one moment leads to the next, that your actions cause outcomes, is built primarily from visual information carried by light. Light creates the raw material from which your brain constructs the story of causality. So yes, light creates cause and effect, but not in a simple, single sense. Light is the foundation, the medium, the carrier, the sculptor, and the revealer of causality. But here's the truly profound realization. Causality isn't a thing that exists independently, which light then transmits or reveals. Causality is a relationship structure that emerges from the properties of light and the quantum fields light manifests. In a universe without light or with light that had different properties, causality would be fundamentally different. The very concepts of before and after, of cause and effect, depend on light being what it is. This is why the question, does light create cause and effect, is so important. It's not asking whether light is one mechanism among many for transmitting causal influence. It's asking whether causality itself, as we understand, is a consequence of light's fundamental nature. And the answer is yes. Let's zoom out even further. What does this tell us about the nature of reality? It tells us that reality is relational rather than substantial. Things don't exist as isolated, independent entities that then interact. Rather, things are nodes in a web of relationships. And those relationships, defined primarily by information carried by light, are what make the things real. You're not a separate self contained within your skin, observing an external world. You're a pattern of information processing, constantly entangling with your environment via light, constructing a model of reality from quantum information, participating in the creation of definite causality from quantum possibility. The boundary between you and world is porous, negotiable, constructed. Light blurs that boundary by connecting you to everything you observe. This should be both humbling and empowering. Humbling because you're not the independent, separate agent you might have thought. You're part of a vast, interconnected web, and your existence is defined by relationships, rather than substance. But empowering, because those relationships include you as an essential node. Without observers, without consciousness processing the information carried by light, the web of causality would remain in quantum superposition, never collapsing into definite actuality. You're not passively observing a pre-existing causal structure. You're actively participating in making causality definite through your observations. Every moment you're conscious, every moment you're observing light and processing the information it carries, you're collaborating with the universe in creating definite causality from quantum possibility. Let me end with a thought experiment that brings everything together. Imagine you're in a dark room and someone turns on a light. In that instant, several things happen simultaneously. Photons begin propagating from the light source, carrying energy and information. These photons establish causal connections. The future light cone of the source expands. The photons carry quantum information in superposition. When they hit your retina, they entangle with your visual system. Your brain processes this information, constructing a conscious experience of seeing the light turn on. In that moment of observation, quantum superpositions collapse, making certain causal paths definite. The very experience of the light turning on is your consciousness participating in the creation of definite causality. All of this happens in a fraction of a second. Light creates causality, conveys it, and reveals it, all in one unified process that includes your conscious observation as an essential component. 2 hours, 51 minutes, and 0 seconds. Final section. Your place in the universe. I want to leave you with a sense of wonder and empowerment about your place in all of this. You are made of atoms that were forged in stars, held together by electromagnetic force as essentially by the exchange of virtual photons. The energy that powers your consciousness comes from food, which got its energy from sunlight through photosynthesis. The information you use to navigate the world comes primarily from light entering your eyes. At every level, material, energetic, informational, you are a child of light. But more than that, you are an active participant in the process by which light creates causality. Every moment you observe, you're collaborating with fundamental physics to make the quantum foam of possibility crystallize into definite actuality. This isn't mystical thinking. This is what the physics tells us, taken seriously. The great physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He meant that the quantum world is so foreign to our everyday intuitions that we may never fully grasp it intuitively. But I think there's something deeper. Maybe the strangeness of quantum mechanics is showing us that our everyday intuitions about causality, time, and reality are the approximations. And the quantum world is showing us the truer, deeper nature of reality. Light creates cause and effect, yes, but it does so in ways that transcend our simple stories of cause and effect. It creates causality as a quantum web of correlations and possibilities, as a geometric structure of spacetime, as a flow of information, as an experiential construction in consciousness. Here's what I want you to take away from this. Every time you see light sunlight streaming through a window, the glow of a screen, the twinkle of stars, remember that you're seeing the mechanism by which the universe creates causality. You're seeing the fabric of cause and effect itself. When you make a decision, remember that you're not just selecting a predetermined future. You're shaping the quantum probability space, participating in the creative unfolding of reality. When you observe the world around you, remember that you're not passively receiving information. You're actively participating in making superposition collapse into definite actuality, creating definite causality from quantum possibility. You are not separate from the universe, observing it from outside. You are part of the universe observing itself, using light as the medium of that observation, creating causality in the very act of observing. And finally, remember this. The next time someone asks you a seemingly simple question, like, does light create cause and effect? You now know that the answer opens up the deepest mysteries of physics, philosophy, and consciousness. Reality is far stranger, far more wonderful, far more interconnected than our everyday experience suggests. Light is the thread that weaves it all together, creating the causal structure that makes reality ordered rather than chaotic, carrying the information that makes observation possible, connecting us to everything we see. You are made of stardust, powered by sunlight, connected by photons, observing a quantum universe that exists in superposition until you look at it. You are magnificent, improbable, and essential. The light that creates causality is the same light that allows you to see these words right now. In this moment, reading this, you're experiencing the very phenomenon we've been exploring, like creating a causal connection between me and you, between these ideas and your understanding, between the past of this video being recorded and the future of you being changed by it. That's the ultimate answer. Light doesn't just create cause and effect in abstract physics. It's creating the causal connection between you and me, right now, through this very experience. And that's pretty amazing. If this video expanded your mind the way I hope it did, please share it with someone who would appreciate it. Drop a comment telling me which concept blew your mind the most. Subscribe if you want more deep dives into the mysteries of reality. And most importantly, go outside today. Look at sunlight. Really look at it. See the photons streaming through space, carrying energy from nuclear fusion 93 million miles away, creating the causal connections that make your vision possible, enabling you to observe and therefore participate in making reality definite. You'll never see light the same way again. Thanks for joining me on this journey to the edge of causality and back. Until next time, keep questioning, keep observing, and keep marveling at the strange and wonderful universe we're part of.